Good morning. Now we have here is a bell ringer that I wrote. It's actually the first question in this actual assignment in the book. And it is best to attempt this problem on paper. So what I would suggest you do is look at the problem, get a piece of paper out, and get to work at it. I'm going to go ahead and read it to you. A railroad system connecting 5 cities is being planned. The goal is to build this system using the least amount of money, while ensuring that each city can be reached by any other city in the system. Based on the distance and terrain, the following chart gives estimates for the cost in hundreds of thousands of dollars to build a railroad between any 2 cities. And as you can see here, we have City A, which is $10,000 to build or hundreds of thousands of dollars. So it's $1 million to build a railroad between A and B, $5 million between A and C, $4 million between A and D, $2 million between A and E. So we want to create a graph model that can cost contained in this table. I'll let you guys work on this for a little while. So I would take the time right now to think about what is your vertex here, what is your edge, and what values to place on as part of the weight for your weighted graph. All right, so go ahead and pause now and take some time to work on that. All right, if you've worked on it, you'll see that you have 5 cities, and you're going to choose the best model here in this table to see which one works best. Okay, so I have the answer on here. I'm hoping that you have drawn something similar to this. As you can see, all you got to do is look and see if the values placed in between each city is congruent to what's in the table. So that edge between city A and city B should be 10. So you can eliminate anything that doesn't have 10 between A and B. So graph 1 has A and B, it has 10. That's a okay graph so far. Graph 2 has 12, we can eliminate 2. Graph 3 has a 10, so we can't eliminate it. Graph 4 has a 5, and that can be eliminated. So we're left with graph 1 and graph 2. So let's go to somewhere else. How about from B to C, which is 7? So B to C here is 5, so we can eliminate 1. If you come over to 3, you see B to C is 7. As you can see, all the numbers are there. We can double check any one we want. C to D, that's here to here, that's 5. How about B to E, which is 11? That's here, that's 11. So graph 3 is your answer. And as you can see, the star beside it proves such. All right, let's move on. Okay, good things. My good thing from last night. The only thing I can tell you is that had no issues going home. I had a really low tire and I still made it home, and I aired the tire up and everything was fine, but I didn't have a blowout. I was kind of worried about that. That's always a good thing when you're trying to get from point A to point B and there's something in between that's stopping you. There you go. All right, minimal spanning trees. Let's talk about that. Let's restate the railroad problem from the bell ringer using terminology associated with graphs. For example, we're going to use vertices, edges, paths, cycles, etc. It says to use finger polling, and that's simple. You vote for one of them, you choose answer 1 with 1 finger, answer 2 with 2 fingers, and so on. So let's say, if we're going to restate the railroad problem, let's look at number 1, see if that works. Remove edges from the graph in such a way that the graph stays connected. Okay. Remember that a tree is something that's connected. 2, remove edges from the graph in such a way that the graph is disconnected and the sum of the final edges is minimal. Okay. That's not going to work because it says disconnected, and that kind of tells you right away we can eliminate that because a tree is connected. We do like the part about the final edges is minimal. The sum of the final edges is minimal. That would be a minimal span. Okay. 3, remove the vertices in the graph in such a way that the graph remains connected and the sum of the final edges is minimal. Now that one works. Let's check and see if 4 is even better. Remove the edges from the graph in such a way the graph remains connected and the sum of the final edges is minimal. I think those are exactly the same. We'll continue on. I'll have to fix that. One of them should say disconnected, but it doesn't. Okay. It says number 4 is right. I guess number 3 is the one I got to fix. All right. Which of the following graphs represents the possible efficient railroad networks and the amount those would cost to build them? Okay. So this is a little more difficult. We'd have to go back to the problem itself and see which one works. What would be the minimal spanning tree? Remember, graph 3 is correct. They all have to remain connected. Now, how do we do that? I'm not sure. But it probably has something to do with using the lowest values possible, right? And still remain connected. Let's see what it looks like. All right. Just because it's the lowest one doesn't mean it's the correct one. Obviously, this 3.9 million over here is probably not going to be it. You got that 10, 11, and 9. That's a lot, okay? That's a whole lot. And I don't think it's 3.9. I think it's 39 million. I don't know where I was getting my numbers from. I don't know. Maybe, maybe not. I don't know. Our best answer, I would venture to say, is probably 1 because it's the lowest. And I was right. But if you notice, graph 4 is an answer that can work too. I wonder why. It's not as low. But the most efficient one would be graph 1. Graph 2 is low, but it's not as low as graph 1. All right. Which rail system leads the lowest construction costs? All you got to do is find out which one costs the least. They say they're the same, but they are the same. Look at that. All right, which answer describes an accurate step-by-step algorithm? That's funny. Algorithm does mean a step-by-step problem-solving situation that someone could follow to arrive at the most efficient rail system or network, given the values of each connecting rail or edge. Step 1, delete the edge with the highest value. Step 2, repeat step 1 until one edge fewer than the vertices remains. Remember we discussed earlier in the lecture that we knew it was an efficient system or an efficient network if the edges numbered one fewer than the number of vertices. So that looks correct, except it says we're starting with the highest value. I think because we can't have cycles, you remember that we probably should start at the lowest. So let's see what it says. Step 1, add the edge with the lowest value unless it creates a cycle. Step 2, repeat step 1 until one edge fewer than vertices remain. You know what? I think that's correct, except no, that probably works as long as everything's connected. Step 3, delete edge of the highest value. We already said that wouldn't work. Step 2, repeat step 1. Number 4, step 1, delete edge until one fewer. No, that's not going to work. So we know that step 2 is the answer. Guess what? We're right. Or I'm sorry, answer 2. Numbers in the following graphs depict the cost associated with building a railroad between cities, represented by vertices. For each graph, which answer on the next slide yields the most efficient network? Look at it carefully. The middles are the same. The outside is not. So for network 1, we'll start with 2. We'll keep it. We'll keep one of the 4s. You don't want both of them because if you do, you'll create a cycle here. You see how you'd have 2 pathways to 2 of those? So we'll use 2, 4, and then we'll go to 5. We wouldn't need this, actually. We would use this 5, and that would connect all of them. So this particular vertex would connect to this vertex, and this vertex. And then that vertex would connect to that vertex. So the total would be 2 and 4 is 6. And then 10, we'd have 16 for network 1. We'll see if that's right. Start with the lowest. Start with the 4. That's going to stay connected. And then the 5 here. And then this 5. Now all we have to do is connect to this one. Okay? Well, it looks like we got a 6 because we've already connected these 3. We can connect that one there. And we have 5, 10, 16, and 20. So let's see if I'm right. Network 1 has a minimal cost of 18, network 2, 12. We already said that's incorrect. I think 4 is correct. Network 1 has a minimal cost of 16 and network 2 has a minimal cost of 20. And I was right. There you go. All right, let's reflect on this. Given any weighted graph like the ones from this activity, does an efficient network of minimal value always exist? Why or why not? Let's see. Answer 1. No, not all networks have both an efficient network and a minimal cost. 2. Yes, since there are several possible efficient networks, each with the total cost associated with it, one must be the least expensive. And that, I believe, is the correct answer. 3. An efficient network always exists when you sum the values of the least costly edges, one less than the number of vertices. Yes, an efficient network does always exist when you sum the values of the least costly edges, one less than the number of vertices. Actually, number 3 is a little bit tricky because you can get the lowest sum with one less than the number of vertices, but you might have a cycle then, and then it wouldn't be an efficient network. So, and 4, no, because remember Harambe. That's right, Harambe's got to poke his little head in all of our little lectures. I think the answer is 2. Let's check. It is 2. Anyway, let's launch. Is there a place in the world that you wish you could go one day? And if so, have you planned how you'd get there? And if you have planned, have you determined how much that planned trip would cost? This actual application that we're learning right now, how to find the minimal spanning tree, is a good means to determine how you can reduce the cost of a long distance vacation trip, especially if you don't know where you're going. So anyway, that's it for this lecture, y'all. Have a ball, y'all. Be blessed and be a blessing.